When we deploy learning-based robots in the real world, they need to be able to autonomously recover when their policy fails, without fully relying on experts. I'm delighted to present our work on correcting high-level robot policies using non-expert feedback. Failing policies can be due to changes in the environment that the robot has not been trained to handle. The availability of objects might change. For example, the robot might fetch an item that is no longer available. Or actions that were previously successful can suddenly lead to undesirable outcomes. For example, the robot may get stuck on a carpet if it has never seen this before during training and hence never learned to avoid it. Typically, such failures require costly expert intervention or substantial time or data to retrain a policy. Yet, certain failures, especially when they happen in everyday context, are also understandable by people who do not necessarily have robotics or programming experience. In such cases, these people or non-experts could provide additional rules to the robot that can help it prevent the failure on future occasions. We are motivated by the question, how can we automatically correct robot failures after deployment using non-expert feedback? Prior work has looked into intuitive ways for humans to teach robots. Learning from demonstration, for example, lets non-experts quickly teach robots new behaviors through kinesthetic guidance. Interactive reinforcement learning is used to teach robots sequential decision-making tasks, for example, using positive or negative rewards, corrections, or preferences. These works highlight the potential of human feedback in reinforcement learning, yet often require teachers to constantly monitor the entire training process. We instead query people only after the failure has occurred. So when we have obtained human input, how can we enforce correct robot behaviors? Constrained reinforcement learning enforces desired behaviors by restricting the state or action spaces, providing penalty rewards, or by interfering with the policy update. However, it requires technical expertise and can often not formally ensure that the undesired behaviors are always avoided. Such formal guarantees are crucial for robots' real-world deployment and trustworthiness. Temporal logics are a popular tool to define formal constraints on robot behavior. With their resemblance to natural language, they balance the trade-off between rigorousness and simplicity for non-experts. While such temporal logic-based approaches are effective, they often interfere with the underlying reinforcement learning problem. For example, they prune actions and paths in the model, which potentially limits the agent's exploration. Rather than directly changing the policy, shielded reinforcement learning restricts the agent's actions. This way, it minimally interferes with the model while still enforcing desired behaviors. Shields can be constructed from temporal logic specifications to define a set of constraints. However, experts are often required to construct these specifications or to turn them into shields, and often an automaton with all possible states needs to be constructed to conduct safety checks. Instead, we apply shields only to the states the agent actually visits, which reduces computational complexity. Taking together the prior efforts from both research fields, we propose to leverage non-expert input in a policy repair approach that automatically synthesizes correction mechanisms or shields to create high-level robot behavior. Specifically, the robot is trained as a reinforcement learning system and deployed in a different environment. Upon failure, it queries a non-expert for a correction that is then translated into a shield, with which the system is retrained. This way, robots do not need to fully rely on experts to resolve failures, and we can formally verify the corrected behaviors. We investigated the following two research questions. Can we use shielding to correct high-level robot behaviors, which we tested through a series of experiments? And if and how can non-experts provide input to correct failures when the robot queries them only after it detects a failure state, which we evaluated through an online study. I'll start with the experiments to answer the first research question and will then talk about the online study to answer the second. We conducted a series of simulated experiments in which we construct shields to create high-level actions in a cooking task from ground truth feedback. We also create shields from incorrect feedback to gain insight into their effect on the failure recovery. This feedback was obtained from the online study, which I will discuss in more detail in a moment. We showcase our approach in a 2D simulated kitchen environment, which is adapted from prior work. In 3 experiments, we collected input for the following types of failure corrections: action refinement, alternative item, and forbidden action. I'll go through each in detail now. Action refinement refines a failed action by executing another action or sequence of actions instead. The agent has been trained to assemble and deliver a salad. However, after deployment, a tomato slice is no longer available. We apply a correct shield that refines the action of fetching a tomato slice with fetching a whole tomato and cutting it into slices first. The incorrect shield refines the failed action by fetching a plate and then fetching a tomato slice again. Our approach converts 30% faster on average and obtained less negative rewards than without a shield. With the incorrect shield, the task is not learned because the shield calls the failed action without solving the issue first. When the agent tries to fetch a tomato slice, it fails again, resulting in an infinite loop of corrections. The alternative item shield corrects the failed action by replacing the missing item with an alternative. The agent has been trained to bake and deliver a cake. However, after deployment, wheat flour is no longer available. The correct shield replaces wheat flour with the alternative, almond flour. The incorrect shield refines the failed action with the following action sequence: fetching a bowl, fetching eggs, and then fetching wheat flour again. Our approach avoids the failure while being more data efficient. It learns the task successfully and converges after 104 episodes on average. Without a shield, the policy is unable to robustly learn the task or obtain positive rewards, even when trained for longer. The incorrect shield again resulted in an infinite loop of corrections, like in the salad experiment that we saw earlier. The forbidden action shield removes undesired actions. The agent has been trained to deliver a coffee. However, after deployment, one floor tile is occupied with a carpet. We apply a correct shield that constrains the agent's behavior such that it never moves onto a carpeted floor tile. The incorrect shield refines the failed action by instead moving one tile down, one right, and one up. Our approach learns the task successfully and converges after 24 episodes on average. Without a shield, the policy does not learn the task and only obtains negative rewards. The line denoted as penalty in the graph shows the results for providing an additional penalty of -1 for moving to carpeted tiles. This extra expert knowledge helped the policy to converge, yet it still requires 25% more episodes and has a less stable learning curve compared to our shielded learning. The incorrect shield performed well. The agent learned that with activating the shield, it actually ends up at the delivery tile. So to summarize, the series of 3 simulated experiments showed that we can use shielding to correct high-level robot behavior. Now let's dive into how we obtained the feedback that we used to generate these shields. We conducted a within-subjects online study in which all 18 participants went through the 3 experiments in random order: the salad, the cake, and the coffee experiment. Participants were 5 female and 13 male and between 20 to 63 years of age, with little to no prior experience with robots and programming. They were provided with an introduction to robot failures and rules to correct them. They saw the agent in its environment and a list of all possible objects, actions, and locations in the environment. They were asked to help the robot by describing what caused the failure and by giving a rule that would help prevent the failure on future occasions. The results showed that the majority of participants could successfully understand and identify the failure, as well as correct the failure successfully. To answer our second question, we found that non-experts can indeed provide the input that is needed for the generation of the shields. So what does this mean? This work is a first step towards a full non-expert policy repair pipeline, and our proof of concept implementation validates for the first time that shields can be used to repair high-level policies after failures. However, we have not yet automated the shield synthesis from human feedback, and we acknowledge important avenues of future work. For example, automatically identifying what is incorrect and correct feedback can be challenging. In the paper, we describe an initial clustering of the open answers based on text similarity. Moving forward, multiple non-experts can be asked to judge whether corrections are sensical before sending them to the robot. Additionally, our results show that incorrect shields might still work well for one specific case, but fail to generalize. We're interested to further investigate how we can automatically test how effective and generalizable corrections are, for example, by validating corrections in a set of benchmark scenarios. Moreover, we conducted simulated experiments, and in next steps, we want to test our approach with the real robot. This means we need to investigate what level of abstraction is needed for the robot's actions and states, with the aim of creating an intuitive interface between low-level robot control and high-level corrections. This also means that we need to explore how we can leverage sensor fusion to provide richer representation of the environment and failure in the robot's queries, so that we can evaluate what information representations help non-experts repair the robot's policies effectively. Our approach is applicable to any sequential decision-making robot that performs common tasks. For example, a robot in a table setting task might place objects according to a set of constraints. Non-experts can specify rules to define desired relations between the objects over time to ensure the correct task configuration. For example, at some point, place the sandwich on the plate. Robots can use on-the-fly non-expert feedback to synthesize controllers to adhere to such rules. To wrap up, we showed that non-experts are able to provide corrections from which shields could be generated, and that shields can be used to repair failures of learning-based robots in a verifiable fashion. As a first answer to our overall research question as posed at the beginning of this talk, what this work showed is that combining non-expert feedback and shielding has the potential for automatic verifiable failure correction. Thanks for listening. If you have any questions, feel free to contact me via the email address listed right here.